Hi, this tutorial will cover the reactions of benzene by electrophilic substitution. So we'll look at the nitration of benzene and Friedel-Crafts acylation of benzene. So your mechanism for reactions of benzene is electrophilic substitution, which involves an electrophile. And you get a substitution where one of the hydrogens comes off and the electrophile is added in its place. So for the first reaction, the electrophile is a nitronium ion. So this is the reaction of nitration of benzene, and this is the nitronium ion, NO2 with a positive charge. Now you need to be aware that the formation of the nitronium ion is part of your reaction mechanism, so you have to write an equation for how this electrophile is formed before you then go on to do your normal Cayley-Arrow mechanism. So to make your nitronium ion, you need sulfuric acid and nitric acid. Okay, so that's the equation that you need to learn. So your nitric acid, which is what's actually reacting with the benzene over in the overall equation, your sulfuric acid, which is acting as catalyst, and this is why it acts as a catalyst, because it generates the nitronium ion, which actually takes part in the mechanism, and at the end we regenerate this, which is why you can consider it a catalyst. So now you've got your nitronium ion, you can now react it with benzene via an electrophilic substitution mechanism. Okay, so here are your starting materials. You've got benzene ring and you've got a nitronium ion. So you've got a ring of delocalized electrons, a high area of electron density in the centre of the ring, and that will be attracted, those electrons will be attracted to the nitronium ion, forming a bond between the benzene ring and the nitronium ion. Okay, now because you have moved those electrons from the centre of the ring, that breaks this ring of delocalized electrons, so now it's only delocalized across these 5 carbons and not the carbon that's taken part in the substitution. So these electrons have moved out to make a bond, which makes this positive overall. So you need to make sure that you have drawn the delocalized electrons going from carbon 2 to carbon 6. And then you need to make sure you've got this positive charge in as well. Now, here's the new bond that you've formed between the nitrogen of the nitronium ion and the benzene ring, but you need to remember that you've also got that hydrogen still on there as well. So now you need to reform the ring of delocalized electrons to put the stability back into the benzene ring. So the bond between hydrogen and carbon breaks, and the electrons from that bond move back into the centre of the ring to reform the ring of delocalized electrons. So that takes the hydrogen away as H+, so you make H+, which will go and react up there to reform your catalyst. And your benzene with your nitro group on it, and the ring of delocalized electrons is reformed. So that's your final product. That is called nitrobenzene. And you also obviously get your H+, so make sure you don't miss that out of the mechanism because that's important. It goes back, gives you a catalyst. But remember, if you're going to draw this mechanism out, the things to make sure that you don't miss are the equation for the formation of the electrophile, the electrons in this unstable intermediate being delocalized across the other 5 carbon atoms, and the plus in the middle of the benzene ring. Just make sure you've got all of those steps, and then that's a nice easy mechanism for nitrating benzene. Now the next reaction we're going to look at is called Friedel-Crafts acylation. It's very, very similar in that you need to remember how the electrophile is formed in the first place, so you need to write an equation. And then the Cayley-Arrow mechanism is exactly the same, so it's nice and easy. So in this case, the electrophile is a carbocation, an acyl carbocation with this C double bond O section here, and this is formed from an acyl chloride reacting with aluminium chloride, so you need to write an equation for that. Okay, so that's the equation that you need to learn. You've got RCOCl plus AlCl3 makes RCO positive plus AlCl4 negative. Learn that equation, obviously being able to change the R group for different alkyl groups, and then that's the starting point for the mechanism, and that is your electrophile for the reaction with benzene. Okay, so now you've got your starting materials again, which are benzene and an electrophile, which in this case is your carbocation. You've got exactly the same mechanism as you've just seen, where the electrons in the benzene ring are attracted to carbocation and attack there. This forms a bond between the carbon and the benzene ring. So we've now got your benzene, you've got that new bond that's been formed, you've still got your hydrogen, and that ring of delocalised electrons is now broken and only goes from this carbon round to this carbon, leaving your benzene positively charged. So that's your reactive intermediate. And then to move on, we have to reform that ring of delocalised electrons. So this carbon-hydrogen bond breaks, the electrons from that bond move back into the centre, and that gives you your benzene with the ring reformed, your carbon, double bond oxygen, alkyl group, and your H+ ion that's come off here. Now, something you do need to know just for the overall reaction equation here, when this hydrogen atom leaves, it leaves and reacts with the AlCl4, which gives you HCl and reforms your AlCl3 catalyst. So again, this is the bit that becomes your electrophile. This is a catalyst that's reformed at the end. This is your electrophile once it's formed, and this is where your hydrogen will go to react to give you your catalyst back. So the overall reaction equation for this is benzene plus an acyl chloride makes this thing here, which is called a phenyl ketone. So it's a ketone here with a phenyl group coming off it, plus HCl, so that bit is also formed, which is not immediately obvious when you look at the mechanism that we've drawn down here. So just make sure that you're aware this is a catalyst and this is also formed as well. And that is it for reactions of benzene. So as long as you understand the structure and bonding in benzene, as long as you understand the electrophilic substitution mechanism, and you can do it for nitration of benzene, and you can do it for Friedel-Crafts acylation of benzene, and you're able to name compounds that contain a benzene ring, then that is aromatic chemistry all done.